Physics-inspired models in artificial intelligence. Hi, my name is Mohammad Ahmad. I'm an affiliate assistant professor in the Department of Computer Science in the University of Washington, Tacoma. I will be giving this tutorial along with my colleague, Sener Ozonder, who's at the Electrical and Electronics Engineering Department at Istinye University in Istanbul. The focus of the tutorial is going to be on how models that originate in physics and how physics in general can help us understand models in artificial intelligence and machine learning. So towards this end, the tutorial is divided into two parts. In the first part, I will mainly focus on and go over foundational aspects of physics-inspired models in AI. And in the second part, my colleague Sener Ozonder will go in more technical detail regarding the relationships between physics models and models in AI. A few words about terminology. So given that physics and AI as a subject in its own right is relatively new, standard terminologies across disciplines is still emerging. So for example, same terms may have slightly different meanings in the two disciplines, like entropy. So whenever we come across such terminologies where they have slight different semantics in physics and AI, so we will call these out. And also for this field as a whole, if you look at the literature, then researchers have used physics-inspired AI, physics-informed AI, physics-aware AI, so on and so forth, to describe the same discipline, or instead of overlapping research endeavors, which are not always exactly the same. So we will not dwell too much on this, but just to call out that this is how the literature is currently. And also we will not dwell too much on the boundaries between AI and machine learning, but mainly focus on the foundations and the techniques and cross-disciplinary connections. So we'll start with the motivation. Why physics and AI? So if you look at the history of physics, so it has a very long history of unifying disparate phenomena and finding common explanations. More recently, there has been some progress in applying physics to understand AI and machine learning, which is yielding very promising results for both disciplines. And especially within machine learning, there are a number of research questions which remain unsolved. And so it is our hope and belief that physics may actually help address some of those problems. And lastly, physics has a long history of combining empirical rigor with theoretical rigor. This is not to say that this is absent in other disciplines, but rather it's relatively prominent in physics. So this is an opinion piece in the journal Science, actually from a physicist, where the physicist calls on their fellow researchers in physics to use their skill set to help understand the challenges in deep learning, or even work towards finding a theoretical foundations for deep learning. So this is something which the research community across disciplines is taking note. And at even a larger level, if we look at some of the newer developments which have been taking place at the intersection of physics and AI, then there is a lot of enthusiasm on both sides, which is evident by some of these recent articles that have come about. That said, one should always take a skeptical eye towards whenever there's a hype, whether it's in the academia or it's in the media, where there are a number of challenges that the machine learning and AI community is facing, which require further scrutiny. So for example, there's a few years ago, there was this well-known, somewhat controversial talk at NIPS by Ali Rahimi, where he described that AI has turned into alchemy for all practical purposes. And of course, there was a rebuttal from other lead researchers. But the point being that The AI and the ML community is facing a set of challenges which require thinking outside of the box. And we believe that physics-based approaches may be one such way to address and foster that kind of out-of-the-box thinking. And even beyond that, that researchers like Yanli Khan, who's certainly one of the pioneers in this area, have taken note, and who himself has a background in physics, that in order to make further progress in theoretical foundations of AI in general and deep learning in particular, we may actually need help from physics. And he gave a series of lectures to that effect last year at Harvard. So now from why physics and AI in general to why this particular tutorial. So it's our experience that, and history also bears out that ideas from physics have time and again provided fodder for conceptual developments in machine learning and AI. So with this tutorial, what we want to do is to provide background and point out synergies between physics and AI for anyone who is interested in the area, who wants to start out and explore commonalities. And so this represents a collaboration between myself, who's coming from a machine learning computer science background, and my colleague Sener Ozonder, who comes from a theoretical physics background. So we seek to approach AI from a physics perspective and physics from an AI perspective and meet in the middle. And that's how this tutorial was born. So the goals of the tutorial can be summarized as follows. So how ideas from physics have informed progress in AI and ML in general, historically speaking, and what are the current developments, explore connections and synergies between the two, and also demonstrate that mapping AI problems to class of physical problems where we already know the solutions and behaviors, it's already possible to do so, and it can help illuminate some of the inner workings of AI and ML models. So when we talk about the interplay between physics and AI, then we can approach this topic across two different axes. So first is the axis of understanding an application. So are we trying to understand the phenomenon, let's say from a theoretical foundational perspective versus taking a more applied approach? And then the second axis being, which direction are we coming from? Are we trying to understand physics from the AI ML perspective, or we are trying to understand AI ML from physics perspective? So the focus of the current tutorial is on the understanding part, but from the physics perspective. That is how physics could help us understand and potentially advance AI. And another thing to emphasize is that what we are suggesting is not something novel or new. AI and ML have always been cross-disciplinary fields. So the genesis of this field in this early era has its foundation in mathematics and logic. If you look at more connectionist type of thinking, then the work of Donald Hebb, which formed the foundations for Hebbian learning, that comes from biology. So that's more than 70 years old. And prior to that, Alexander Bain came up with a very similar connectionist architecture independently, almost a century before that. And if you look at almost anything within machine learning, for example, it has its roots in statistical methods, things like Lindermeyer system, which were developed to describe growth of behaviors of plants, were actually used subsequently for describing grammars. There's a whole field of biologically inspired computing, the most famous example being ant colony optimization. If you look at Bayesian, more recent techniques like Bayesian rule list, they has its roots in statistics, frequent pattern mining, and even functional analysis in social networks. Within the domain of explainable AI, we have the shape framework, which uses shapely values, and that actually comes from developments in game theory from the 1950s. So continue on the theme of why physics and AI. So the physics-inspired models, we believe, do offer us possibilities to address some open and pressing problems in AI and ML. So understanding black box models, improving deep learning models in data-poor domains, and challenges that we are currently facing in domains of transfer learning and active learning. And many of these, of course, translate into more efficient models which reduce cost of training, for example, or even deployment. So the goal is that perhaps these synergies, these insights could lead to more efficient algorithms and models. In general, there is a call in the community, especially from more well-established researchers, regarding the need for new ideas. So this is not to deny that tremendous progress has been made over the last decade or so in terms of just the number of publications and the number of people who are working in this area. But that said, researchers have also noticed what is being touted as the decrease in level of empirical rigor. And it seems that, so in a well-known paper, the researchers pointed out that a lot of recent progress is incremental algorithmic progress in nature. And one of the reasons is that for a lot of empirical studies, problems become challenges to be solved instead of focusing on developing new insights, new ways of looking at the world. So just to highlight this, so here are examples of some recent, over the last few years, large-scale studies where it was shown that the supposed progress in the AI/ML side was somewhat illusionary. So in the first one, so a large-scale comparison of GANs revealed that if one is given sufficient compute time and parameter optimization, even quote-unquote bad models can outperform quote-unquote good models. And if you take tasks like sequence-to-sequence learning models, then it's actually possible to beat state-of-the-art by doing hyperparameter tuning on just simple baseline LSTM models. Even in terms of the architecture for study on certain encoder-decoder style networks, demonstrated that if you have a very simple attention-based model, that could actually outperform much more sophisticated architectures. And the story goes on and on. Even in something similar has been observed in Bayesian deep neural networks, which seem promising at a time, where it is possible to actually use simple baselines to be the state of the art. And of course, there's subsequent work with respect to these where people have tried to remedy these, but this problem as a whole still exists. So a possible rebuttal to this is what I described is that, well, we are living in a different era. Science has evolved. So we look at the trajectory of science. We have where initially what was just theoretical science, empirical science. We also have the computational paradigm, and more recently, people talk about the data-driven science or the fourth paradigm, all of these being complementary to each other. So this notion that if you have data, then you do not need theory. But it turns out that after the initial enthusiasm regarding this particular notion, that's actually not true. So issues regarding data deluge and being overwhelmed by data and not being made sense of theory, it's not new. I mean, John Tukey was talking about this more than 50 years ago, and here we are. So one always needs theory to understand what's going on. And the reason is that theory-based models, they encapsulate causal or cause-effect relationships, which are often derived from first principles. So data does not technically talk or speak for itself. There's always a lens of theory which is present. And so this actually, folks who have been working on this in this area for a while would recognize that there was a debate to this effect just over a decade ago regarding is the data deluge characterized by big data? Is that leading to or going to lead towards the end of theory? And as our experience in the last 10 years have shown, that is actually not the case, because big data needs, well, big theory. So to illustrate, consider the example of Google flu trends. Where this, and after a widely publicized paper was published in Nature arguing that Google flu trends do not work as intended. The reason being that if you look at the forecast prediction by what Google's models were predicting versus reality, there is a differential of sometimes overestimating by twice, and in general over predicting. And so this was held as especially by the media, for one to talk about trial by media as an example of why these data-driven models do not work. However, if you look at researchers who actually were going to use this data for flu prediction, then it turns out that, and here's the direct quote, that Google flu trends is the only source of external information with statistically significant forecast improvement. So it's not that the model does not work, or it's more like the model does not work in its own right, but if you combine this with more traditional models, it turns out that this ensemble model actually works better than just having a more agnostic model. So from here, we move on to one of the problems which is facing machine learning these days, which is proliferation of models with massive number of parameters. So we take a lesson from the history of physics. So consider the following. So it's actually a common misconception amongst a lot of people that one of the reasons that the Copernicus's heliocentric model with sun at the center won out from the geocentric model that the Earth is at the center of the universe is because it had more predictive power. So it turns out that for almost a century, the older geocentric model actually had an advantage in terms of predictability of more complex astrophysical phenomenon. The reason that the Copernican model initially won out was because of the following. It was a much more simpler and elegant model. In modern parlance, we would say that it has very fewer parameters as compared to, say, the geocentric model. And if you take a larger view of history, then we observe the following. So after Copernicus came up with this model, Tycho Brahe made detailed observations about the orbits of the planets, which was then used by Johannes Kepler to derive laws known as the three laws of planetary motion, which were very model agnostic, that they did not provide any foundations with respect to why that particular behavior was being observed, but it did provide a mathematical formulation. And almost a century later, from the time of Tycho Brahe, that Isaac Newton unified all of these phenomena and a host of additional phenomena by just set of two sets of laws, the laws of gravitation and laws of motion. So, which brings us to the current context. So if we look at like some more recent, extremely well-performing models, let's say like GPT-3, so we're talking about tens of billions of parameters, translates into billions of dollars. And yet, if you take a very similar view from physics, that you're focusing on looking towards things which we can generalize, the underlying principles, then or perhaps we can find ways to summarize things in a much more succinct manner. Which brings us to a brief history of physics and AI. So as I mentioned earlier, so there's a long history of ideas from physics permeating and inspiring progress in AI and machine learning. A very relatively less known fact is that the Kalman filter, which is one of the most widely used algorithms in computing, actually has its roots in physics. Even MCMC methods, they were developed to address problems in statistical mechanics in the 1950s. Statistical physics-based approaches for low-rank matrix optimization have their roots in physics, became very popular in the 1980s, and again, after the rise of massive social networks in the early 2000s. And also for stochastic block models, which are widely used in clustering, so they have their roots in spin glass theory. And in the field of deep learning, so if you look at formalization of autoencoders and Hopfield networks, what we observe is that there was actually a lot of interest from the physics community in the 1980s when connections between autoencoders and spin glass theories were discovered by physicists. And we will go over these in much more detail in the second half of the tutorial. Boltzmann machines, as the name shows, they also have their roots in physics. They were invented to add stochasticity to networks to avoid them getting stuck in local minimum, which was the problem with the standard formulation of Hopfield networks. And so if you look at more recent developments, so information bottlenecks, again, coming from the physics domain, or at least having inspiration from there, offer as possibility to understand deep learning, certain types of autoencoders are very closely related to techniques which are used in signal processing in physics. And there's also been work in incorporating loss functions using differential equation constraints from physics within the deep learning models themselves. So a lot of work in that direction towards this goal. So with some of the foundational framework laid down and a historical overview, so now we move on to some of the larger topics that we are interested in. We'll start with the generalization in physics and AI. So it's well known that generalization is a fundamental challenge in machine learning. And it's partially because more often than not, generalization also requires, let's say, access to massive amounts of data or having a theoretical understanding of the underlying phenomenon. So if we contrast that with physics-based models where they're mostly not data dependent, and when such models capture the underlying phenomenon, they perform extremely well on unseen data, even on data from different distributions. And physics-based and theories and predictions from the physics domain have shown to be correct in certain domains like particle physics to have correct prediction, even to the order of, let's say, 8 to 10 decimal places, which is quite remarkable. However, if we look from the machine learning side, then, well, the existing learning theories, which are mostly based on considering worst case packed learning scenarios with generalization bounds, then we are unable to explain the success of deep learning. Why should it be successful at all? Again, with the disclaimer that there has been some progress made in this direction, but not a whole lot, or not as much as we would like. And yet deep learning works really well in practice. So now a classic paper comes into mind. So understanding deep learning requires rethinking generalization. So what is really interesting about this work is that so the researchers, they started with deep learning networks, and for the outcome variable, so instead of using a real variable, they just fit random variables. That is, they generated random labels and fit a model into that, and they observed a number of things which somewhat at that time seemed somewhat counterintuitive. So, for example, regularization, or at least explicit regularization, may improve generalization, but it's actually not necessary or sufficient for controlling the generalization error. So going back to the experiments that these researchers performed. So again, we are looking at models with a massive number of parameters. And what they're observing is that they are able to fit the new models, these models with this new fake data, so it's just random noise. CNNs are able to fit these models as good as simple data. And the results are really puzzling. So what exactly is going on? So here's a summary of their some of their results and observations. That generalization is not happening because of the learning algorithm or because the hypothesis space is restricted or because of algorithmic stability. And as I mentioned earlier, even regularization is not really contributing towards this. It's better to conceptualize it as a hyperparameter that is useful in fine-tuning. It's actually the inductive bias which is somewhat influencing generalization. So maybe there are some models which are likely making use of massive memorization in combination with learning low complexity patterns. But it's somewhat counterintuitive results. So from generalization, we move on to computational complexity. So for the benefit of people, researchers from the physics background who may not be familiar with computational complexity, so I'll first define some foundational concepts, so which would be familiar for the overwhelming majority of computer scientists. So in a very simplified way, computational complexity theory is concerned with the question of what are the decision problems for which efficient algorithms exist. And so we address problems like studying complexity classes, which are basically a set of problems of related complexity. In general, a large number, if not most, and definite but not all, complexity classes are defined by three main characteristics. So what is the problem type? So is it a decision problem? Is it, for example, an optimization problem, so on and so forth? What kind of model of computation is being used? Turing machine versus, say, non-deterministic Turing machine, Boolean circuits. What are the resource bounds in terms of runtime, in terms of let's say, memory available, so on and so forth? So this goes back to what was classically known as the Einschlägung's problem, that given an input, answering yes or no according to whether the statement is universally valid or not. It's a well-known problem in the domain of mathematics. So there are connections between these two. And in the interest of time, it's it would suffice to state that, again, mainly for the benefit of physicists in the audience, that it's a major area of research in theoretical computer science. And there are known hierarchies of these complexity classes that computer scientists are interested in. So there are a few which require special mention. So a class of problems which can be solved in polynomial time. So they're what are known as the SP, the complexity class P, and ones which can be solved in polynomial time by non-deterministic Turing machines are what are known as the complexity class NP. And another class of interest is recursively enumerable. So these are problems which for which, let's say, a yes answer can be verified by a Turing machine in a finite amount of time. So we are taking this detour, which may not seem relevant at first, but the dividend towards the end will show that show connections across several domains within computing and physics. All right. So we talked about the polynomial class, and so there's another subclass for complexity known as the Boolean satisfiability problem, or SAT. So it's the problem of determining if there exists an interpretation that satisfies a given Boolean formula, and that there exists actually a polynomial time many-to-one reduction from the Boolean satisfiability problem. And within that, there is this 3-SAT complexity class, which focuses on satisfiability of a formula in conjective normal form. So made up of these horn classes, where at best we have 3 literals within each class. And so satisfiability, for the benefit of the physicists, is defined in terms of, can we replace these literals with true and false so that we can come up with a universal class where this formula is always true. So in the late 80s, early 90s, there was a spate of interest from the physics domain in understanding some of these complexity classes, which yielded some interesting results. For example, so it's been observed that, so for the class of 3-SAT classes, a complexity class, a phase transition is observed. So think of a phase transition as how suddenly states of matter change from one phase to the other. So solid, liquid, gas. So the phase transition is observed that there is so if we plot, say, the ratio of clauses to variables and the probability of finding a satisfiable solution, then there is a particular point where the possibility of finding such solutions rapidly decreases. And so this phenomenon is very similar to what we observed in phase transitions in physics. All right, so that's one interesting result coming from the physics domain. And so beyond that, again, this is another detour that we have to take. So we start with, not with physics, but with mathematics. In 1976, mathematician Alan Cones conjectured that it should be possible to approximate many infinite dimensional matrices with finite dimensional ones. A few years after that, in the physics domain, Boris Sarlson conjectured that the tensor product and commuting operator models of entanglement were roughly equivalent. So details for the computer sciences in the audience, the details are less relevant. Other than that, so entanglement is a phenomenon which is observed in um, in elementary particles, or a group of elementary particles where the properties of these particles are entangled in the sense that we cannot measure the properties of these particles, of individual particles, without measuring it for the entangled particles, or for the groups of entangled particles. All right, so this is where things get really interesting. So it was shown that, so there's another class, complexity class, known as the MIP star class, which is defined as follows. So it's the class of problems that can be verified through interactions with entangled quantum provers. And it is equivalent to the class of recursively enumerable complexity class. So if these two are equivalent, then, well, both the Seidelson problem as well as the Kahn's embedding conjecture, they are false. And earlier this year, it was demonstrated that these are indeed false. So the implication is remarkable that that these seemingly unrelated problems in mathematics, physics, and complexity, computational complexity in computer science, they have a common solution. That is, proving or disproving one leads to important applications in the other two. So from generalizability to complexity, now we move on to interpretability and explainability in AI and machine learning. So before we go into the relevant concepts in physics, it is important to describe that there are multiple notions of interpretability and explainability in machine learning and AI. So concepts which do not have exactly the same meaning, but rather overlapping meanings. And in layperson's terms, one way to describe this is that your model or your system, it's understandable to a human with domain expertise, say experts in natural language, within the particular context and use case. So for example, if you look at this equation on the right, standard model Lagrangian. And so if you show this to a physicist, and so she may say that, well, my 4-year-old could understand this, but for the majority of us computer scientists, it may just be just a group of Greek symbols. So context, domains, application matter. And also we have to look at explainability from not just from the perspective of model, but at a system level. So system has its constituent parts as the solution, as the user, whereas a solution could be made up of, say, the features, the algorithms, the parameters, and of course the model itself. And so the user, we have to take into account the person's domain knowledge, their cognitive capacity, and what level of granularity is the explanation needed. So the explanation that you're giving to a 5-year-old would be very different from, say, what you're giving to a person with, say, a PhD in physics. And so there are a number of properties or characteristics of explainable AI which have been identified in literature. That is a tutorial in its own right. But in the interest of time, we will describe a few which are of interest. So the first one is simultaneity. That is being able to understand the whole model simultaneously. So if you look at this example at the bottom right, so the decision tree B has this property, or at least has it much more as compared to decision tree A. And then there's decomposability. That is, each component is admissible with respect to an intuitive or easy explanation. So where this idea is that, so for example, in general, when we think about interpretability, then naturally we think that regression models are much more easier to interpret as compared to deep learning models. But suppose the deep learning models are using relatively simple features like these, which have intuitive meaning versus complex, highly engineered features like these, then if the deep learning model is using the intuitive features versus regression model is using these engineered features, then the dichotomy does not hold. And lastly, there's this expectation that that the models comes with certain performance guarantees and or convergence. So now moving on from the domain computing side to mapping explainability to physics. So the idea is that an explainable model from the physics perspective, so it should be grounded in theory, and the hope is that it's more likely to safeguard against learning of spurious patterns because the theory and physics would presumably encode constraints around these patterns within the theory itself. And so the question is, how can one use insights from physics to understand such models? So to illustrate, so we will use models which are inspired from physics. And so a few disclaimers are in order. So these actually do not cover all possible types of models which one can envision where physics-inspired models could be used to create better algorithms or improve models. But rather, we are just restricting our current discussion to particular domains. So these models are especially useful in data-limited domains where large-scale data collection lags behind theory. So the problem is that how can we use or constrain algorithms to leverage domain-specific physics knowledge, which satisfies certain principles? So, for example, conservation of momentum or conservation of mass, so on and so forth. So which brings us to work on physics-informed neural networks, where the idea is that so we use these for the purpose of the classical tasks that we use neural nets. But we can incorporate certain things like, let's say, certain laws of physics. For example, say nonlinear partial differential equations. And there are different ways to do this. Taking a more theory-based approach versus a more data-driven approach. One limitation that these models has is that in general, they're designed for very specific tasks or groups of tasks. An ideal situation would be where if we can identify architectures that would be capable of adapting to, say, variations in the correctness of physics, quality of training data. So this work is still in infancy. Some progress has been made. So for example, in the form of work on autophysics, which focuses on automatically finding optimal architectures for physics-based models. And complementing that is work in physics on what the authors call physics-guided neural networks. And so they take this, tackle this problem from three different perspectives. So one is that a more traditional approach, which is that feature engineering is informed by theories and domain knowledge from physics. Second is that adding physical constraints. So for example, let's say add regularization term to punish overfitting what is known as the physical inconsistency term. So when you optimize physically inconsistent results, and we'll look at an example of that shortly, are minimized. So the goal is that to have a model which is readily interpretable and also does not violate constraints in the real world. That said, there are a few issues one should be mindful of, or things things from domain which can actually be helpful in creating such models. So for example, in physics domain knowledge can be used in parameter initialization. So it can help, it's been shown that it can help in, say, not getting stuck in local minimas. We can also define priors, which can be used to constrain the search space. Another way to do that is to also define what are admissible values. And so that can also guide the optimization direction. And you can even further constrain the optimization problem by defining physically consistent classification boundaries. All right, so to illustrate, we are going to use the following example. All right, so the task is that, so we have to build a model which can predict water temperature as functions of depth and time for a lake. So there are already physics-based models that exist, so the general lake model. And so it captures the physical processes by, for example, capturing certain relationships, like let's say it's known that denser water sinks, and to which corresponds to the relationship between water temperature and density. And so say if the model predicts the higher density for a point closer to the surface, then, well, that's physically inconsistent. So that said, the real world is much more complicated. There are a host of features with respect to, say, the weather, composition of water, and other factors which affect what is actually recorded and observed. So within the loss function, so we can actually incorporate this, that whenever there's a consistency, then we punish the model. And when the consistency higher, then the model is punished more. And it's not just keeping into account pairs of points, but we have to look at all recorded pairs of points. So that's why we are taking the max over all pairs and dividing that by the number of pairs when creating the loss function. And so we can also control the relative importance of minimizing the physical consistency. So this is analogous to multiplying the average physical inconsistency with a hyperparameter. And if you really think about it, that's very similar to how we think about regularization parameters. So these are the results from two different lakes in Minnesota, lakes Mendota and Lake Mille Lacs. So the main thing to focus is the physics-based models. So this is the classic physics-based models. Quantities are defined, so the predictions are not going to be to vary from a particular value. And results from just using the data, the features, using a neural network, and then a neural network which is using results from a generalized model, and the physics-guided neural network approach that I just described. And so the remarkable thing is that not only in terms of physical inconsistency, so we of course do not get any physical inconsistency in the physics-based model, as well as the proposed model, but the adder itself is actually much less than just using a purely physics-based model. So that's another argument for merging of these two approaches. So from illustrating an example to now we move on to open questions in neural networks and deep learning in general. So consider these questions in this slide. So why don't heavily parameterized neural networks overfit the data? What is the effective number of parameters? Why doesn't back propagation get stuck in local minima? Um, and so if you think about these are very modern, relevant questions for 2020, and yet uh, these are questions, open questions from a paper by Bremen from 1995. So 25 years later, we are still wrestling with the same questions. And to this, we'll add that that why do neural networks approximate functions well in practice? That is, why do they work so well in general? Um, uh, so before we delve into some of these, so a few things require special mention. So although many techniques in AI and ML have their origins or inspiration in statistical physics, um, a physics-style theory of deep learning does not exist, however. There are some attempts here and there which have yielded interesting results, or what I like to call gleams of gems, but there's no meta theory that exists right now. All right, so we will start with this work by Henry Lin, Max Tegmark, and Rolnick, where they try to address at a very high level the question of why does deep learning work well in practice. So their argument is as follows. This is coming from the three researchers from the physics background. So the laws of physics constitute an exponentially tiny fraction of all possible inputs. And if you look at the practical applications of AI and deep learning, that also constitutes a tiny fraction of all possible data. And so these data sets, they are generated by some statistical processes. And if these processes have a certain hierarchical form, then deep learning models, they are likely to be more efficient than shallow one to model them. And their reasoning is that if we go from data to, say, very high level phenomenon, in physics and at the corresponding level, if you look at, this is of course a Y example on the right-hand side. And if you look at, in the computing domain, the problems that we are trying to solve, that there is a quote unquote, a natural hierarchy in terms of concepts and connections between different levels of granularity that exists. Because that is constrained, that is possible to be captured by a deep learning network because it can be described in a certain form. So that's an extremely high level way of looking at things. More closer to theory is some recent work on information bottlenecks and neural networks. So the theory of information bottlenecks has been around for a while. So the idea is that, so when information is flowing through certain types of architectures, and again, this is not just applicable to deep learning networks, but to a host of other networks, that when information is traveling, then through the process of information bottlenecks, information is summarized. Extraneous information can get lost, so that only the relevant information is preserved. So what do we mean by that? So basically what we are doing is, what the process does is identify the most informative features and remove extraneous ones. So in the parlance of information theory, what we are doing is that we are minimizing the distance between the mutual information of the original data and the compressed version with respect to the target variable. All right, so let's explore this. Before exploring this in a little more detail, so I'll first talk about the inspiration behind this. So just over a decade ago, it was observed that a special case of deep belief networks work exactly like renormalization, where renormalization is a technique which is used in physics. So think of this as coarse graining over, say, certain descriptions of certain details of a system. It's mainly to avoid infinities and being able to compute the overall state of the system. So in few years after that, two biophysicists, Schwab and Mehta, they applied deep belief networks to a model of a magnet at its critical point. And what they discovered was that the network automatically used the renormalization like procedures to discover the model state. So that spark of inspiration became the foundation of Tishby's work on deep learning and information bottlenecks. So Tishby had worked on information bottlenecks prior to that. So here's the experiment that he and a student performed. All right, so start with the neural network. The task is binary classification. So assign random initial weights and observe how the network evolves. And so for each, for different layers in the network, so compute, say how much information there is. And what they observed was that over the course of iterations, the network converges to the information bottleneck theoretical bound. So it seems that the network is actually learning some minimal representation. So we can think of this as moving from one layer to the other as learning the different hierarchies of concepts. So this, in a little more detail, this is what's going on, that within each deep learning network, when you move on from the previous layer to the next, some information is getting lost. And yet, information with respect to the target variable, so that is still being preserved. And we can divide this in this whole process in terms of memorization and compression. So at the beginning of the informational bottleneck process, so what the network tries to do is that if you look at the number of bits that the network is storing, it either remains constant or it's roughly or slightly increases as the network changes its connections to encode the patterns in the input data. And this is very similar to, our researchers have described this as being analogous to memorization. But after some time, the network starts to lose information and it only keeps the features that correlate strongly with the target variable. So what's going on over here? So one way to think about this is that, so each iteration of the stochastic gradient descent, the network updates the strength of the connections via the random walks. As the network cycles through training examples, it might forget weaker correlations. So as a real world example, consider the following. So suppose we have, let's say, a toy model that seeks to learn cats versus dogs, recognize them in images. When we initially build the model, it's going through training examples and it sees that dogs are always in front of, let's say, dog houses. And so it learns that as a feature. But over the course of time, it encounters new examples where the doghouse is not present. And so it starts to forget those correlations. So which brings us to another example, the committee machine. Uh, so this corresponds to this terminology corresponds to, especially in the 1980s and early 90s, the researchers especially in the physics community, working at the intersection of neural nets and physics, looking at certain type of ensemble methods. So that's where the terminology comes from. So we're going to consider, or many of these consider the simplest version of a two-layered neural network. The weights in the second layer are fixed to unity or 1. So this is your standard task of the target variable and dimensional sample and weights connected to each layer. And the particular setting is what is known as the student-teacher approach. So the labels are generated by feeding IID random samples to a neural net, which is the teacher. The output then gets presented to another neural network, which is the student for training. And so from this physics community, a number of results on this somewhat simple model have been observed, which may have, if they could be generalized to other neural networks, can hold very promising results. So one thing which was observed, interesting result, is that so if alpha is the sample complexity, then we observe that alpha spec is a critical value where there's a permutation symmetry between hidden neurons that remains conserved even after optimal learning. And remarkably enough, the learned weights of each of the hidden neurons are identical. But beyond that particular value, the symmetry no longer holds. And the reason for that is that as each of the hidden units correlate strongly with the corresponding hidden units of the teacher. And again, another remarkable thing being that the optimal generalization error can actually be described in terms of the sample complexity. Again, going back to the theme of phase transition, so it's also observed that the optimal error corresponds to a particular weight configuration. And that weight configuration is the same for every hidden unit. And if you think about it, that would actually remind one of a simple regression model. And also going back to the specialization threshold, that when the number of units exceeds that threshold, then what we observed is that the different hidden units learn different weights, which actually improve the generalization error. And there's also what is known as the hard phase, where we do see that we can get good generalization from at least from an information theoretical perspective, but not necessarily from a practical perspective as the number of hidden units goes. So which brings us to the area of GANs. So those in the audience who may not be familiar with GANs, so these models, generative adversarial networks. So they formulate the problem of building neural networks as a two-player non-cooperative minimax game in the sense of game theory. So it has two sub parts. So one is the generator. It's a model for generating new examples and a discriminator, which discriminates whether the example of real and fake. If you have seen any deepfakes, then you would be familiar with these models. So using a host of variety of settings in addition to that. That said, the classical formulation of GANs, they do suffer from a number of issues with respect to, uh, let's say, instability, mode collapse, and having a lack of reliable metrics to determine the quality. So a variant of GANs which is of interest is what are known as Wasserstein GAN. So the difference is that instead of in the previous formulation, instead of a discriminator, we have a critic. Instead of saying that reject or accept as real or fake, the critic scores the realness or fakeness of the data which is generated. The motivation behind this is that the generator should minimize the distance between the training and the generated data distributions. And so this point is very important. So taking that as the foundation, some physicists came up with the Banach-Wasserstein GAN, which is a generalization of Wasserstein GANs, which actually allows the practitioners or people who are using GANs to select the features to emphasize in the generator. So the idea behind the Wasserstein metric was that we're looking at the distance of distribution, probability distributions in the images, and so we can, if we extend this to this Banach space, then we can generalize this notion and create much better models. As a side note, we can actually extend these to more traditional metric spaces, but in practice, that does not seem to work as well. And of course, in addition to that, there has been work in incorporating stochastic differential equations into the architecture of GANs, having solvable models of GANs, so on and so forth. So continuing the theme of deep learning, so there is some work with respect to the challenge of over-parameterization in deep learning. So the challenge is that the number of parameters has been observed in deep learning. It scales with data, which translates into cost of training, as we talked about at the beginning of the tutorial. It scales, so it's a product of parameters and number of data points that we are dealing with. Computational products in an ideal, the computation requirements ideally are quadratic, but in practice they are much more, because in order to get linear improvement in performance, you actually need data which scales much faster than linearly. So that is a problem of cost. Okay. So to illustrate, we are going to use a couple of examples. And but first, the reason that this is a problem is that, so we actually don't have a good theoretical understanding of relationship between performance, model complexity, and computational requirements for deep learning architectures in general. And the other remarkable thing, we also alluded to this earlier, is that in practice, these models, if this was a more classical setting for machine learning models, this would result in overfitting, but this does not happen. So here an example of some models and their number of parameters. And so the number of data points that we are dealing with, it's just 50,000, and performance is increasing. We are not incurring loss in terms of, let's say, overfitting. An extreme example is the noisy student model, which has 480 million parameters, while ImageNet only has 1.2 million data points. Let's consider this example. So we start with corrupting the training labels by replacing them with a random label. So for example, in this case, replacing with this is 8, but we randomly mislabel it at 0. And so what we observe is that the test accuracy actually does not degrade as much. And if we actually have early stopping in our model, then the test accuracy is actually pretty remarkable. So which means that the model is learning something. Here's another overview of that. Is that as even with a 50% label corruption, we do get overfitting, but if you look at the training data, but the performance is remarkably good with respect to the test accuracy. So there's some sort of learning going on. Okay, so now putting some of these things together. So one is that, so what is going on? So ideally what we want in a real world setting is to be in a scenario where we have reduced the computational complexity, we have models which generalize better. And so the hope is that physics may offer some help in finding these alternative architectures which can integrate physics knowledge into these models. And we can use, and there has been some progress in this regard with respect to the marriage of, say, symbolic approaches with more traditional connectionist approaches. So to conclude this section on physics and deep learning, so there are multiple points of intersection between physics and deep learning. There is great potential to advance theory and practice, provide theoretical foundations, and of course, save money. So in the second half of the tutorial, so my colleague is actually going to discuss some additional points of synergies in much more technical detail than I did. So that brings us to another set of models, the stochastic block models. So the block models have their origin in social network analysis, where the idea is that we're given large graphs and we want to detect communities in these graphs. So think about detecting communities in, say, Facebook or Instagram, social networks. And also to model such networks. And it was discovered that the standard formulations of these, they actually do not, are not able to replicate real world networks. So an additional constraint was added, so hence the term stochastic block models, where the constraint being that we also give an asymmetric matrix of edge probabilities which describes probabilities of being connected from one community to the other. So for example, if this is our network, then each blocks correspond to a particular community. So connections within the community versus connections across communities. So a lot of work in this area also has its roots in physics, again, especially in the 1980s, and a renewed interest in more recent times. And so there are a few key results that I'll mention. Is that what the physicists observed and discovered was that it's possible to determine the optimal performance and identify regions or parameters where such performance can be reached by belief propagation algorithms. And again, going back to the theme around phase transitions, that there's a separation between phases, which is characterized by where it is possible to clustering where it is not possible to do so. So that was an overview of some models. So now we move on to limitations of these physics-inspired models. We start with an ideal scenario where, so ideally physics physics may provide foundations for AI models and deep learning and machine learning models and approaches. So if we just focus our attention to hybrid approaches, then, well, parameters still need to be calibrated. It's possible to overfit. They may be computationally expensive. The physics models may be incomplete, mainly because of there's this thing known as the scale accuracy trade-off that is at different scales. We have to use approximate models, which may result in biased models. So that's a known trade-off. There's limitation with respect to solvability. So many physics-based approaches, so they deal with toy models because that can yield elegant solvable solutions. Mapping this to the machine learning domain, so like it's possible to, for example, describe and formulate let's say error estimation, but the disadvantage being that mainstream learning theory in computing actually deals with worst case bounds. So an ideal scenario would be if these two approaches could be combined, if there's a way to make them complementary. Another limitation is, at least for a subset of models, replicating model behaviors. So generalizing these to models for which very interesting detailed results which are present, let's say committee machines and student-teacher settings, to much more complex architectures. And also to replicate aspects of the models which are observed in practical applications and practical architectures. And related to that is letting go of certain assumptions. So that's a problem which also exists in machine learning. So model the data no longer as IID, but as some other way. So there has been some research in this area in the last couple of years. And then there's, of course, the problem of generalizability, at least for certain class of physics-inspired models that I alluded to earlier, that they are for specific tasks and class of problems. So ideally what we want is models which can work with different levels of correctness, with noise, data missingness, and other data limitations. And also for certain extremely complex phenomena like complex adaptive systems, traditional physics-based approaches have limitations. So for example, trying to model and understand extremely complex phenomena like society, whole economies. So in those domains, we have what are known as complex adaptive system approaches, which understandingly actually take their inspiration from physics also. And so the ideal scenario in this case would be, again, to take a top-down, bottom-up approach from both directions, from physics and AI, which could address certain problems. So to conclude the first half of the tutorial, so AI and physics have a long history of interaction and cross-correlation. AI and machine learning face a number of challenges, and with challenges come opportunities. So there are a lot of opportunities which are available for collaboration and progress. The synergy between physics and AI offers potentials to gain insights into the foundations of AI and even bring advancement in AI with, say, new algorithms and new modes of thinking. So in the second half of the tutorial, so my colleague will go over uh, synergies between physics and AI at a more fundamental, foundational level and with greater theoretical rigor. And so if there are any follow-up questions, even after this tutorial, please feel free to email either one of us. And additionally, we also maintain a project website with a set of resources, with a survey of the field, conferences, relevant research work, research agendas. You're more than welcome to check those out. Thank you.